I want to put together a little video today, particularly for those who are absent due to the field trip. I'm going to start by looking at a problem very similar to one that we did in class yesterday. We had compared one that was very similar to this yesterday to 1 over x squared dx from 1 to infinity, knowing that that's one of the integrals of the form 1 over x to the p with p is equal to 2, and that converges. And we started by looking at the range of values, the output for the sign, which is -1 to 1. Because my numerator is sine of x plus 1, I'm going to add 1 to this inequality. And then I need an x squared in the denominator. Now, if we're going to use direct comparison test, then the relationship that we wanted to show was that this integrand would be less than this one, so that physically we could see that this function is below this function. So the argument that I'm going to make today with this particular situation is twofold. Certainly, if 1 to infinity 1 over x squared dx converges, then pi to infinity is going to converge, and then 2 times that will converge as well. So now I'm looking at this function compared to this one, and this one again. Now this, we have established the correct inequality relationship, so I know that the integral 1 plus the sine of x over x squared evaluated from pi to infinity will converge by the direct comparison test. On Tuesday, or I guess that was Wednesday, we spent a great deal of time developing and proving the direct comparison test. Today we're just going to, I'm just going to present to you the limit comparison test without any proof, do a couple of examples for you. But again, pointing out to you that the whole purpose is we have some integrals that we just don't know how to integrate. And maybe they don't even converge. So if there's, we can make a comparison with some integral for which we know it converges or diverges, then we can establish whether or not there's a purpose, or in practice it would even be reasonable for us to consider some kind of approximation technique. The limit comparison test says that if I have two functions, f and g, that remain positive on the interval a to infinity, I can evaluate the limit of the ratio of the two functions, and if I get some constant between 0 and infinity, then in terms of the integrals, they're either going to both converge or both diverge. It is extremely specific that I have to get a constant between 0 and infinity. Not 0, not infinity. Those two, if the result is 0 and infinity, it is inconclusive. It does not tell me anything other than that. The first function that we're going to look at, I'm actually going to do three ways. The first, which is an integration technique, because I do recognize this as an inverse trig antiderivative. I'm going to rewrite this. The limit as b goes to infinity, 1 to b, 1 over 1 plus x squared dx. So hopefully you would have recognized that too, and that would have probably been your first means of approaching this problem. Now I've got the limit as b goes to infinity, inverse tangent of b minus the inverse tangent of 1. As b goes to infinity, that angle is pi over 2 minus pi over 4. The angle whose tangent is 1 is pi over 4. And since I got a value, I got a finite value for that integral, I know that that indefinite integral converges. I'd also like to do the direct comparison test, just as a review from what we did yesterday. I'm going to compare again to 1 over x squared from 1 to infinity dx, because I know, again, that is the form 1 over x to the p with p equals 2, and that does converge. In order to make a conclusion with the direct comparison test, I know that there is an appropriate inequality relationship that must be established. And in this particular case, because this is the one that converges, it physically has to be greater than the one on the left. So I must convince myself, or you must convince yourself, that that relationship indeed is true. So certainly x squared plus 1 is greater than x squared. But what happens when I take the reciprocal? And I'll just look at this numerically. I know that 3 is greater than 2. When I take the reciprocal, what happens to this inequality relationship is that it changes direction. It should change the direction here as well. We're not multiplying or dividing by a negative or anything like that, which would make us reconsider that. Since I have established the relationship that I wanted to, I know that 1 plus 1 over x squared dx converges by the direct comparison test. And sometimes that's all I'm asked. Even if I could integrate, I'm just asked whether or not it converges. Finally, I'm going to use the limit comparison test using the same function to compare it to, 1 over x squared, again because I know about that. I know about that integral. I know what it does. Before I begin to evaluate, I'm going to do a little bit of algebra. And I get, when I try to take that limit, I get an infinity over infinity, so I'm going to do L'Hopital's. 2x over 2x, reduce that. That is 1. That is certainly a constant. Therefore, by the limit comparison test, this integral, 1 to infinity, 1 over 1 plus x squared dx, converges. So quickly, I'd like to do, at least for this video, one more, taking a look at 1 over e to the x minus 1. Yesterday, we evaluated 1 over e to the x, and that seems like something logical to compare it to. And we found that that converged to 1 over e. I'm not going to work that out again. I'm going to let you check that from yesterday. So if that converges, then again, I must show that 1 over e to the x minus 1 is less than 1 over e. To do that, I'm going to start by comparing not 1 over, but just e to the x minus 1. And certainly, to e to the x. Mistake here. I wanted to show 1 over e to the x minus 1 to be less than 1 over e to the x. Certainly, e to the x minus 1 is less than e to the x. When I take the reciprocal, though, as we saw earlier, that's going to change the direction of this inequality. So this, at least, the comparison of these two functions using the direct comparison test is not going to work for me. Now, theoretically, there should be some function that I could find and I could establish the correct relationship. I thought the obvious one was 1 over the x. That didn't work, so now I'm going to try the limit comparison test. Take the limit as x goes to infinity, 1 over e to the x minus 1 over 1 over e to the x. Again, a little bit of algebra before I try to do anything else. I've got an infinity over infinity situation. L'Hopital's is going to end up as infinity, or e to the x over e to the x. Now that seems never ending, but what I'm going to do instead is I'm going to simplify that is equal to 1, so the limit as x goes to infinity of 1 is 1. 1 is certainly a constant between 0 and infinity. Therefore, on the bounds 1 to infinity, the indefinite integral 1 over e to the x minus 1 dx converges. And that was by the limit comparison test.